Hello students, welcome to Sri Jayendra's Rank Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 9 of a unit system of particles and rotational motion. So let's begin with today's class. In today's class we are going to discuss about the rolling motion of an object. So let's begin then. First of all, when I say rolling motion of an object, I'm talking about the translatory motion plus rotational motion of an object. So when any of the objects say that it is rolling, that means it is having a translatory motion plus rotational motion. If it is having a such kind of motion, we can say that object is rolling. I hope this is clear. So when I say translatory motion, I mean, let's suppose this is the horizontal surface, this is one of the wheel, and this wheel is moving in this direction, then all its particle is moving in this direction. Suppose something like this. Then this could be said as the translatory motion of an object. Let's call it as a VCM, and this all particles are moving with the speed of v. When I say that it is in rotational motion, then I must say that it is rotating around its axis of rotation. Let's suppose it has been hinged over here and it is rotating such like this with angular speed omega. Then if I see the tangential speed of all this will move in this. Again, that should return as an r omega. This should be written in r omega. This is r omega in this direction, it's a negative x direction, and this is r omega in positive x direction. And if I add this to whatever I am having is the rotational motion, is the rolling motion, I'm sorry. Is it clear? Is it? So do you understand what we are supposed to do? Rolling motion is not new to us. Yes, we have done a translatory motion. We have started it in almost in the motion in straight line, and up to work power energy we have studied a lot about the translatory motion. In this unit, in the 7th unit, we have studied a lot about the rotational motion. Now we are not going to do anything new. We are just adding this, that if an object is performing simultaneously both the motion, then I will say that it is rolling. It is as simple as that. So can we do this? That what rolling is and how supposed to it should behave? Is it clear? Is it? So let's begin then. The rolling motion of an object. It's a rolling motion of an object. So the situation would be that this is the wheel and this is its center. Let's suppose it is performing translatory motion. This is VCM. This should be the VC. This should be the V. It's a velocity. This should be the velocity. This should be the velocity. This should be the velocity. This is the translatory motion. This is the translatory motion of an object. Yes. Now let's suppose it is having a rotational motion as well, that here it is rotating with speed r omega. This particle is r omega. This particle moving in this direction having a speed of r omega. This particle is moving in the this direction, it's an r omega, and this particle is moving in this direction with a speed of r omega. Yes, this is the rotational, this is the rotational motion of an object. Now I'm going to add this, that I'm going to add that translatory motion plus rotational motion. So the situation would be something like this, that this was my wheel, and now it is having this as a VCM. At this particle, it is having two components. One is the V, another is the r omega. For this particle, two components, one is the V, another is the r omega. For this particle which is touches the ground, this will be having a two components, which is V and r omega. For this particle lying on this periphery, it's a V in this direction and it's an r omega in this direction. So does it clear? Does everything is clear? Are you sure? Are you? Now let's just discuss the special case when we say that our object is in pure rolling motion. So in the case of a pure rolling motion, we can say that V should be equals to r omega. Yes, and a, or I should say, a tangential acceleration should be equals to r alpha. So V would be equals to r omega, and tangential acceleration at, that should be equals to r alpha. So if I put this in this situation, my wheel should be having motion like this. Let's have a look very quickly. Yes, this was the wheel, this is its motion, this is VCM. Now and I should say this is V, this is r omega. So this is V, this is V. So effectively this should be root of 2V. This is having a zero velocity because V is equals to V. Yes, one is moving in the positive x direction, another is representing the direction in the negative x. Both are having same magnitude. It would be a V minus V, that would be 0. About this is V, again this is V. So that should be equivalent to root 2V, and this is V, this is V, it's a 2V. So we can say that a particle which is at the top of the surface of the sphere, or we can say top of the surface of an object, is having twice of the velocity, while the particle which is in contact with the surface will be having a zero velocity. And for rest of the other all particles, you can calculate by using vector's law of addition. So does it clear what we are supposed to do? Does it? Are you sure? Great. Now let's look the same thing according to the acceleration. So let's have a look. Let's suppose this is the situation. This is a wheel, this is its center. Yes, this is the ACM. Yes, acceleration of center of mass. This is the particle, it is moving in this direction with a particle in this direction A, this particle in this direction A particle in this direction A. This is the translatory motion. This is the translatory motion of an object. I hope this is clear. It's a translatory motion of an object. Now let's say a second one. This is the center. This is moving in this direction with r alpha. If it is the r alpha, this would be in positive x direction, which we call as an r alpha. This then we can call it's an r alpha. This particle is moving in this direction, r alpha. This particle moving in this direction, r alpha. This is the rotational motion of an object. This is the rotational motion of an object. If I am supposed to add this to, then what I can have is, it would be the rolling motion, which is having a combination of translatory plus rotational motion. So this would look something like this. This was the situation. Now we have already discussed that for pure rotational, we can always write V is equals to R omega and AT or A equals to R alpha. So when we can say this, we can write this, it's an A, it's an R alpha, this is R alpha, this is A, this was A, this was R alpha, this was R alpha, this was A, and this center is moving with a speed of moving with the acceleration of ACM. So if it is moving with, the situation is something like this, then if I produce a vector addition of this, if I do the vector addition, then I will be having something like this. Let's have a look very quickly. So this, let's replace A and R alpha. Yes, this would be twice of acceleration, both are in same direction. For this particle, this is A, this is R alpha. So if I understood or as an A, this is root of 2A. If I am talking about this, this is A, this is A, this will be the root of 2A. Now what about this? If you look at this, then this will be having R alpha in this direction, 80 in this direction. So at this point, AT is equals to 0, but please mind well that your particle is moving in a circular path for sure. Yes, and when any object is moving on a circular path, we must understand that it must be having a centripetal acceleration. So acceleration, or I should say centripetal acceleration, would be in this direction. I hope this is clear. For every particle, AC would be there. It is not the thing about only this. Yes, it is not we are not talking about that only the particle which is in a contact with the surface having an AC. No, it is not like that. But at this point, at the point which is in contact with the surface, we cannot say that acceleration equals to 0. It would be a non-zero. Yes, unlike this, when we were discussing the same case with the velocity, we used to call it that at the bottommost point, or we can say at the point where particle is in contact with the surface, velocity would be 0. It is not the case when we talk about the rotational motion or rolling motion, and we are talking about the acceleration. I hope this is clear. So is it clear? So what you need to do is, you do not need to do anything extra, anything additional. What I need to do is simply I need to add translatory motion, and I need to add the rotational motion of an object. If I am able to do this too, then yes, I can roll the object for sure. I hope this is clear. Yes, so let's just see this. The total kinetic energy of rolling body. So what I want the total kinetic energy. Why total? Because I know that my particle is going to have translatory motion, as well as my particle is going to have a rotational motion. So my particle is having both the motion. It would be having a translatory motion, it would be having a rotational motion, and when I add this two, it is the total kinetic energy. While I say total, it means it is the kinetic energy of the rolling body. I hope this is clear. So when I write kinetic energy of translatory system, it's in half mv square. And when I say rotational kinetic energy, then I must say it's in half into I into omega square. So this is equals to half into m into v square plus half into I into omega square. Let's just solve this. It's in half mv square plus half into, as we have discussed, the moment of inertia could be written as m into k square. Yes, k is the radius of gyration. Yes, and omega can be replaced as, look at this, we have the relation v is equals to r omega. According to this, I can replace this with v by r. So this could be written as v square by r square. While I write this, I take half into m into v square as a common, and I have been left with the 1 plus k square by r square. This is the kinetic energy of a rolling body, or I should say it's a total kinetic energy. Does it clear? Does it clear? Does it? I hope this is clear. Now what about the k square by r square? So what I understood is that, let's suppose it is the case of a circular disc. It is moving, that is having translatory motion as well as rotational motion, something like this. So its moment of inertia is m r square by 2. I need to compare it with the mk square. So for that its k square by r square should be equals to half. This is the case of the circular disc. Do you understand this? Yes. So now let's have some other objects. Let's say ring is there. Its moment of inertia is mr square. Let's suppose I'm comparing it with mk square. So k square by r square is equals to 1 for the ring. Let's say for the hollow sphere, the moment of inertia for the hollow sphere, yes, it's a 2 by 5 mr square. Comparing it with mk square, I'm having k square by r square, which is equals to 2 by 5. Solid sphere, let's say this is equals to I is equals to 2 by 3 mr square. Yes, I'm talking about that they are rolling about their zz axis. Yes, but for the spheres everything is zz because they are the dimensional. So it depends on us that from where we need to observe this, and which diagonal I have chosen. Yes, which diameter I have chosen. So this is equals to I is equals to mk square, and for that k square by r square, that should be is equals to 2 by 3. Yes, let's write it down for the hollow cylinder. For this, it's an I would be equals to mr square by 2, and when it is mr square by 2, let's compare it with the mk square. Yes, it is rotating about the axis of the cylinder. So it's a k square by r square. This is equals to 1 by 2. A solid cylinder, its moment of inertia would be equals to mr square by 2. I made a mistake. Hollow cylinder, it's an mr square only. So it's a k square by r square. It's a k square by r square, which is equals to 1 only. For solid cylinder, it is mr square by 2. And this would be equals to I is equals to mk square. It's a k square by r square is equals to 1 by 2. I hope this is clear. So if you look at this, everything, this is 1, this is half, that means 0.5. This is 1 by 2, it's a 0.5. This is 1, 2 by 5, it's a 0.4. 2 by 3, it is approximately 0.66. Let's assume it as a 0.6. So when I arrange this, in a order such that object having the least k square by r square to the object having the maximum number of k square by r square. So 0.4 is the least one. 0.4 is the least one. So this is k square by r square. It's a hollow sphere. Then it would be a 0.5. 0.5 would be with disk as well as solid cylinder. Then I would be having a 0.66. It's a solid sphere. Then who would be the next? First it was hollow sphere, then it was disk and solid cylinder, then it was the solid sphere, and at last it would be the cases of 1. It's a hollow cylinder as well as ring. I hope this is clear. Is it clear? Yes. So this is required. This is in the ascending order. Lowest would be the first, highest would be the last. So this is about k square by r square. Now let's back to the kinetic energy which we were discussing. That total kinetic energy of my body would be something like this. It would be half mv square into bracket 1 plus k square by r square. This is the total kinetic energy of the system, of the rolling motion. I hope this is clear. Is it clear? Have you noted it? Have you noted it down? Please do it, please. Have you? Great. So now let's just suppose the examiner has asked me that find out kinetic energy of ring when it is in rolling motion. So what I'm supposed to do is that kinetic energy of the rolling body should be is equals to half mv square into bracket 1 plus k square by r square. This is the case of a ring. And when this is ring, it's a k square by r square. That would be equals to 1. So if it is equals to 1, what I can write is it's an half mv square into bracket 1 plus k square by r square. It's a 1. So this would be equals to half mv square multiplied by 2. This 2 has gone, and this is equals to mv square. I hope this is clear. Is it clear? Are you sure? Can you do this? Can it be done? Can it be? Ready for the next question? Are you ready? Then let's have a look. The question is that find out ratio of translatory kinetic energy, translatory kinetic energy to the total energy for solid cylinder. So what do you want? You want the ratio. You want the ratio of the translatory kinetic energy to the total energy for the solid cylinder. So what I'm supposed to do is, I understood the translatory kinetic energy, that would be equals to translatory kinetic energy, that would be equals to half into m into v square, and the total energy would be equals to half mv square into bracket 1 plus k square by r square. If I took a ratio of this, this would gone, and I have been left with only the 1 upon 1 by k square plus r square. So it's a translatory kinetic energy divide by total energy, that would be equals to 1 divided by 1 plus, it's a solid cylinder. So for solid cylinder, k square by r square is equals to 1 by 2. It's a 1 plus half. So this is equals to 1 by 3 by 2, and which should be equals to 2 by 3. Did it? Great. Yes. Yes. Can you do this? Can you do this? Are you sure? Great. Next question. The questions can say that what fraction of total energy is associated with rotational kinetic energy when solid sphere is in rolling motion. So this is the question, that what fraction of total energy is associated with rotational kinetic energy when solid sphere is in rolling motion. So how will I do this? What I understand is, what I want, it's a rotational kinetic energy to the total kinetic energy. This is the requirement. Now while I say rotational kinetic energy, I mean I'm talking about the half I omega square divided by total kinetic energy. It's a half mv square into bracket 1 plus k square by r square. So this is equals to half into I is the mk square multiplied by omega, it's a v square by r square, divide by, it's a half mv square into bracket 1 plus k square by r square. So if I check this, it's a half can gone, m can gone, v square can gone. So I have been left with the k square by r square upon 1 plus k square by r square. I hope this is clear. When I say it's a k square by r square upon 1 plus k square by r square, it's a solid sphere. For solid sphere, this k square by r square, that should be equals to 2 by 5. So this is equals to 2 by 5 upon 1 plus 2 by 5. This is equals to 2 by 5 divided by 7 by 5, which comes to, it's a 2 by 7. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. So can you do this? Can it be done? Can it be? Are you sure? Can it be done? Let's move for the next question. Let's suppose the situation is something like this, that spring is there and spring is having a spring constant of k. We have, let's say, a hollow sphere is there moving in this direction. So the question is, find out maximum compression of spring if initially hollow sphere is in rolling motion. So what I want the rolling, I want the maximum compression of the spring. And while calculating the maximum compression of spring, while what I want is that the object will be in the rolling motion, and it is going to collide with the spring. It will give its energy to the spring. The energy in the spring will be in which form? Yes, which form? Yes, it is in the elastic potential energy that we used to call it as an half kx square. And when hollow sphere came to a rest, then it is the maximum potential energy stored in the spring. So this is the situation I should proceed with. So let's call as an energy conservation. This is location 1, this is location 2. I can write it's a total energy of first, it's a total energy of 2. When I say total energy, I mean it's a potential energy 1 plus kinetic energy 1. That should be is equals to potential energy 2 plus kinetic energy 2. Potential energy 1, at the first location spring is in the natural length, and when the spring is in natural length, I must say potential energy would be the 0 plus kinetic energy. Now they say it is in the rolling motion, so I must write it's an half mv square into bracket 1 plus k square by r square. That is equals to potential energy 2. In this situation it is half kx square. This is the maximum compression of the spring. It's a half kx square plus kinetic energy. Here it will be at rest. So this could be written as this is 2, this 2 has gone. This is mv square into bracket hollow sphere, it's a 1 plus hollow, it's a 2 by 3. Yes, that would be equals to k into x square. While I write this, it's an mv square multiplied by 1 plus 2 by 3. This is 5 by 3, that is equals to k into x square. So this x square is equals to 5 by 3 mv square divided by k, or I should say x is equals to root of 5 by 3 multiplied by mv square by k. This is the maximum compression of the spring which is possible. I hope this is clear. So now do you understand what rolling motion is and how can I do it? Yes. So let's find out some certain other parameters, and let's find out certain other situations with the rolling motion. So let's suppose this is the case of the wedge, and we are going to discuss the rolling motion on the wedges. So when we say a rolling motion, let's just quickly revise this, that we understand that motion of a rolling body on horizontal surface is the combination of the linear motion and rotational motion. Yes, when we say rolling motion, when we say that object is rolling, we understand that the all points of the rolling body must be having same angular speed but different linear speeds. And one more thing, when a body rolls on a surface, when the surface has a frictional force, then the torque will act on the rolling body due to the frictional force only. Now let's suppose look at this situation, that in this situation an object is in rolling and it has started from here and it is going to be ended over here. While this height is h and this surface is with friction. I hope this is clear. So initially we are going to discussing the rolling motion of an object on the sphere, on the for the sphere on the wedge, and that wedge contains a friction. I hope this is clear. Is it clear? Is it? Great. Now let's look at this. When I say that body has been released from here, it's a u equals to 0. This height is h, this angle is theta, and it is moving in this direction, and this wedge is with friction. Let's say coefficient of static friction is mu. So, or coefficient of friction is mu. So what I'm supposed to do is that this object is moving, that means in the rolling motion, and at certain point of time it will be at this location. So let's just check it out, that which all forces are acting and what would be the situation. So if I understood that which are the forces, this will be the mg sine theta, and this will be the force of friction, and as it is moving in this direction, this would be its acceleration. I hope this is clear. Yes. So let's check it out, different parameters when object is rolling on the wedge having friction. Let's get this. Let's first look at the velocity of the sphere when it reaches at the foot of the wedge. It is in the rolling motion, and this wedge is having a friction. So what could be done? What do you think? What I understood is that we can have a energy conservation. We can have an energy conservation at two locations. That this is my location A and this is my location B. While I say energy at A and energy at B, this is total energy at A, that should be is equals to total energy at B. While I say total energy, it's in kinetic energy at A plus potential energy at A, that should be is equals to kinetic energy at B plus potential energy at B. So kinetic energy at A would be 0 because it has been released from the wrist, plus potential energy at A, it's an mgh, this is taken as a reference, this would be the h equals to 0, this would be the mgh, that should be is equals to kinetic energy at B. Now please at this point the energy will be equals to energy due to rotational motion plus energy due to translational motion. So this is the combination of rotational plus translational that we call as a total kinetic energy, and that total kinetic energy would be equals to half mv square into bracket 1 plus k square by r square plus potential energy at B, that would be equals to 0. I hope this is clear. So if this is clear, I can write it's an mgh, that would be equals to half into mv square into bracket 1 plus k square by r square. So this has gone, and I am having v square equals to 2gh. V square is equals to 2gh upon 1 plus k square divided by r square. This is v square. I hope this is clear. If I want the v, it would be the square root of this. It's a root of 2gh upon 1 plus k square by r square. Does it clear? Does it? So this was the velocity when it has been reached to the bottom of the, or we can say at the fit of the circle, width of the wedge. I hope this is clear. Is it clear? Is it clear? Any doubts up till now? Do you have any doubts? Are you? Are you having anything? No? Great. Now, I'm interested in one more thing. Let's have a look. The situation is something like this. This was the wedge, and this was an angle theta. This wedge is having a friction. Yes, and this block has been released. Sorry, the sphere has been released from here. It's a u equals to 0, and it will be reaching over here. Yes. So when this is the situation, let's study all the forces that is acting on this system. So what I understand is this is the force that we call as an mg sine theta. In the upward direction of the wedge, a friction would be there, and this is moving in this direction, so acceleration would be in this direction. So if I consider that all the forces acting in the direction of motion. So what I understand is that in the direction of motion, one of the force acting, it's the friction. Yes, it's in parallel or anti-parallel I am talking about, and the another is mg sine theta. Now two forces are there, one is the mg sine theta, another is the friction, that I understand. But what I want is that does mg sine theta can provide a required torque for a rolling motion? Does mg sine theta can provide required torque to the body? Can it? My answer would be no. So what I understand is torque due to mg sine theta would be equals to 0. Or torque due to friction would be equals to friction multiplied by radius. It's an F into R. So what I understand, a very very important aspect of this motion is that it is the frictional force. Which makes body in rolling motion. I hope this is clear. Yes, because when I say it is in rolling, I must understood that it must be having a translatory motion, and it must be having the rotational motion. So when I say that if friction is there, rotation is possible, and such rolling is possible. If no friction is there, no one would be there to provide the torque. And if no one would be there to provide the torque, that means, do you understand? Yes, it means that no one would be there who can provide the rotational motion, who can provide the torque. That means it will be having only translatory motion if no friction is there. Great. Now let's just understood the parameters one by one, and while we will keep in mind that it is the friction that will make it a rolling motion. So it was initially at here, finally at here. This angle was theta, this is at h, and we understand that this is having a friction. It has been released from this. We have already derived the velocity. Now it's a turn for the acceleration. So what we can understand is, let's suppose this distance is x. So we can write like this, it's a v square minus of u square, that would be equals to 2ax. Initially it was at rest, so, and finally we have the velocity that is equals to 2gh upon 1 plus k square by r square minus of 0. This is equals to 2 into a into x. So this would be the 2gh upon 1 plus k square by r square. That should be is equals to 2 into acceleration into x. Now x, I am going to replace this x because no one will give me the x. Always the data would be given in terms of the h. So as I understand this triangle very well, it's a sine theta is equals to h by x. So this x could be replaced by h by sine theta. Let's just replace this as this a multiplied by x is equals to h by sine theta. So I have been left with it's a gh divided by 1 plus k square by r square. That should be is equals to a into h divided by sine theta. So this h and this h has been gone. I have been left with the acceleration, that is equals to g sine theta upon 1 plus k square by r square. This is the acceleration, and you can see this is the constant acceleration. Yes, g is the constant, theta is always a constant. If you have fixed your body, and it would be always the case that you are going to fix your body, then k square by r square is constant. So this is a motion having uniform acceleration. I hope this is clear. This is a motion having uniform acceleration. It is not a variable acceleration, and as it is having the uniform acceleration, that means we can always apply kinematic equations for uniformly accelerated motion. I hope this is clear. Is it clear? Is it? Great. Now let's work for the time required to reach the foot of the wedge. So this was the theta, this was height h, this is with friction. So what I'm supposed to do is that this distance was x, and I know that this is u equals to 0. So what I can write is that let's just replace it's an x is equals to half a t square. This is x is equals to half into a would be, we have derived in the previous slide, it's a g sine theta upon 1 plus k square by r square multiplied by t square. So let's just replace the x. We have this, it's a sine theta, that would be equals to h by x. So this x could be replaced by h by sine theta. While I am replacing this, I can have this, it's a h by sine theta, that is equals to 1 by 2 into g sine theta upon 1 plus k square by r square into t square. So this t square should be is equals to, this t square should be is equals to 2h by g sine square theta into bracket 1 plus k square by r square. I hope this is clear. Yes. So this t could be written as this is of root 2h by g sine square theta into under root of 1 plus k square by r square. I hope this is clear. Is it clear? Are you sure? So now we have a velocity, we have a time at which it will reach at the bottom of this fit. We have the acceleration. Yes, we have all these three parameters, and let's just write it for a summary purpose in a one slide, and we will discuss something very important. This is theta, it has been released from here. It has been reaching here with certain velocity. So first, that velocity was root of 2gh upon 1 plus k square by r square. Second, this is with friction, and this is height h. Yes, second, it's an acceleration. So this is a is equals to g sine theta upon 1 plus k square by r square. And third, it's a time period, which is equals to root of 2h by g sine square theta into bracket under root of 1 plus k square by r square. So if you understand that, let's suppose everything is constant, only objects are changing. That means we have, let's suppose, a ring, we have solid sphere, we have disk, we have hollow cylinder, we have solid cylinder and everything. And they ask me that which one would be having the highest velocity, which one would be having the lowest velocity and everything. That all kind of questions could be asked. So how will you do this? How I can do it? So what I understand is that, let's look at this very carefully. This is a very good question. This is 1 under root of 1 plus k square by r square. This acceleration having again 1 plus k square by r square, again inversely proportional, and for time it is directly proportional, root of 1 plus k square by r square. So those object having k square by r square higher, it will require a larger amount of time. It will require a larger amount of time to reach at the bottom. Again, if those object having higher amount of k square by r square, that would be having lesser amount of velocity. So I hope you can connect it, that if k square by r square is higher, it means the time is higher. Why time is higher? Why time required is higher? Because their velocity is lower. I hope this is clear. Now you can connect it. Great. Let's talk about the acceleration. If k square by r square is higher, r square is higher, their acceleration would be the lower. I hope this is clear. So if let's look at this. If ring, solid sphere, hollow sphere, and disk all are having same mass and same dimensions, are being released from wrist, from top of the wedge. Arrange their velocity so arrange them according to the increasing order of their velocity, time, acceleration. Go through the data very carefully. Go through it. They say that they have 4 objects. They are having the ring, they are having the solid sphere, they are having the hollow sphere, and they are having the disk. And all these objects are having the same mass, and they are having the same dimensions. That means the radius will be the equal, their area would be equal, definitely their so they are having a same mass and same dimensions are being released from wrist, from the top of the wedge. Obviously this wedge is having a friction, so they says that arrange them according to the increasing order increasing order of their velocity, time and acceleration. Yes, so let me mention it. Wedge is having friction. Yes, so now what I supposed to do, what can be done? First, what I understand is velocity, it's an inversely proportional to the 1 plus k square by r square. Time, directly proportional to the 1 plus k square by r square. Acceleration, inversely proportional to the 1 plus k square by r square. Yes, for ring k square by r square, it's a 1. For disk, this is 1 by 2. For hollow sphere, it's a 2 by 3, which we can call as a 0.6. This is 0.5. And for solid sphere, SS, yes, it's a 2 by 5, which is 0.4. I hope this is clear. So now I understood that the object having higher k square by r square will be having the lower velocity, and I want to arrange them in the increasing order. So it would be the least would be the first. So least velocity would be having an higher k square by r square. It's a velocity of ring. Then it would be a velocity of hollow sphere. Then it would be a case of velocity of disk. Then it would be the case of velocity of solid sphere. This is their velocity in the increasing orders. Let's work for the acceleration. You can observe this, that even in the acceleration, k square by r square is in inversely proportional. Only the difference is this is in square root, and for acceleration it is having the power of 1. So the order would be the same. Higher the k square by r square, lower would be the acceleration. So it's an acceleration of ring, then it's an acceleration of the hollow sphere, then it's a acceleration of disk, and then it's an acceleration of solid sphere. Now about time. For time, higher the k square by r square, higher would be the time. Lower the k square by r square, lower would be the time. So I need to arrange them in increasing order. So least would be the first. So least time would be of solid sphere. Yes. Then it is for the disk. Then it is 1 second. Yes, I have made a mistake. It's when I say least, it is less than this. Yes, so velocity of solid sphere is at the maximum. Yes, now it is correct. So least time would be of solid sphere. Then time required would be the disk would require greater amount of time than the solid sphere. Then it would be the we can say next would the solid sphere has gone, then disk has gone, then it's an hollow sphere, and then it would be the ring. Ring will take a maximum amount of time to reach at the bottom of the sphere. I hope this is clear. Is it clear? Is it? So can you do this? Can you do this? Are you sure? Okay, great. Now let's talk about the friction as well, and all those information which is essential. This was the situation. Yes, this is theta, this is h, and it is with friction. This is x. If required, I will use this. In this direction, mg sine theta is acting, and in this direction, a friction is acting. It is moving in this direction, so I must understand that mg sine theta minus of friction is equals to m into a. While I write this, I can understand that this is mg sine theta minus f should be equals to m into acceleration. Its value of acceleration, that is equals to g sine theta upon 1 plus k square by r square. So for the friction I could write this, it's an mg sine theta minus of mg sine theta upon 1 plus k square by r square. So this could be written as mg sine theta into bracket 1 minus 1 by 1 plus k square by r square. This could be written as, this is friction, that is equals to mg sine theta into bracket, this is 1 plus k square by r square minus of 1 divide by 1 plus k square by r square. Yes, so this one and this one has over. This could be written as mg sine theta into bracket k square by r square upon 1 plus k square by r square. This is the friction. This f is equals to mg sine theta into bracket k square by r square upon 1 plus k square by r square. I hope this is clear. So when I write this, this f is equals to mg sine theta into bracket k square by r square upon 1 plus k square by r square. Now what about the friction? What is the value of this? I understood that when block is moving on the wedge, I can write like this, it's an f is equals to mu s into n. If I took for the maximum value of mu s, maximum value of the friction, sorry, so this could be written as mu s into mg cos theta. Yes, this is mu s into mg cos theta. If this is the maximum value, this is f max. Yes, we can always call this as the limiting friction. Yes, so this f max, that could be written as mu s into mg cos theta. If I equate this to, let's talk about the maximum friction, then it could be mu s into mg cos theta, that is equals to mg sine theta into bracket k square by r square upon 1 plus k square by r square. This mg has gone, and this mu s is equals to sine by cos, it's a tan theta into bracket k square by r square upon 1 plus k square by r square. This is mu s. You must remember that this formula as well. This is the mu s. It's a coefficient of static friction required for the rolling motion to each and every individual object. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? So if I find out the mu s for every individual object, let's talk about the mu s for ring, then it would be the tan theta into bracket k square by r square, it's a 1, divide by 1 plus 1, it's a 2. Yes, this is for the ring. This would be something like this. Yes, it's a tan theta into 1 by 2. This is equals to mu s. Same way you can find out for disk, same way you can find out a holy sphere, solid sphere, and everything. Does it clear? Does it? So now do you have any query, any concern over this? Is there anything? Is there? No? So now we know the value of the friction and magnitude of the friction and mu s and everything. The one thing I have been left is direction of friction. Let's have a look. So this was the situation. This is theta, this is h. Initially my object was here, finally it is at here, and this is having a friction. Yes, now we know this that this object rotates, or as rotate it can roll due to force of friction only. That means if no friction is present, object will have only translatory motion. So if no friction is possible, if no friction is possible, if no friction is present, then my object will be having only translatory motion. I hope this is clear. Is it clear? Is it great? Now direction of friction. If object is moving in this direction, friction is acting on this direction. One of the surprising fact is, if even though object is moving in the upward direction, its direction of tendency would be in negative x direction. So this is the f external, and if this is the f external, the friction would be in this direction. So one of the facts, or you can remember it according to the thumb rule, that direction of friction direction of friction is in upward direction whether object is moving in downward direction or upward direction. So whether object is moving in the downward direction or whether object is moving in the upward direction, the direction of force of friction will be always in the upward direction. Does it clear? Does it clear? Any doubts over this? Is there anything else? Is there any doubts? Are you sure? So does this concept is crystal clear? Are you sure? Are you? Great. Let's look for the question. This is one of the wedge having height h, angle theta with friction. One of the object is there, it is reaching here, and while it has been reaching to the foot of this wedge, its acceleration is a1. Now we have another wedge having same dimensions, that means having height h, having an angle theta, but having no friction. It's a mu equals to 0. It is having certain friction. A same object has been taken and it is going to be reached at this position. At this time its acceleration would be a2. Yes, I hope this is clear. So what I want is find out ratio of a1 is to a2. So when object is moving on a wedge having friction, it can roll, and when it is having the rolling motion, their acceleration could be written as this: a1 should be equals to 2g sine theta upon 1 plus k square by r square. When object is moving on the smooth wedge, it could not roll because it is only mg sine theta, that is equals to m into a. So this a is equals to g sine theta only here, or a, yes. So the acceleration in this case a2 could be written as g sine theta. If I take a ratio of this two, this is a1 is to a2, this is equals to g sine theta upon 1 plus k square by r square into 1 by g sine theta. This would be, this has gone, only the term that I have been left with, it's a 1 upon 1 plus k square by r square. This is the ratio of the a1 is to a2. I hope this is clear. Is it clear? Shall I extend this numerical? Let's look at this. The question says that in the previous question, find out ratio of v1 is to v2 and t1 is to t2. So first is the case having a wedge having friction, and second is the case that is the wedge without friction. When I write v1, that is equals to root of 2gh upon 1 plus k square by r square, and when I write the v2, that would be equals to, without friction, that means it will be having only the sliding motion, that is it is having only the translatory motion. This v2 could be written as root of 2gh. If I took a ratio of this two, it's a v1 is to v2, that is equals to root of 2gh upon 1 plus k square by r square multiplied by it's a 1 by root of 2gh. It is something like this. I hope this is clear. So this and this has gone. This is equals to under root of 1 by 1 plus k square by r square. This is equals to v1 is to v2. Have you done this? Have you? Are you sure? Can it be done? Now let's work for the time period. So now let's work for t1 is to t2. So t1 was with friction, that means t1 was the case when friction were there, and when friction were there, the time period when friction was there, the time period was written as that it is the t that should be is equals to t1, that should be is equals to root of 2h by g sine square theta into bracket root of 1 plus k square by r square. The case of rolling motion. Now a second case when no friction is there. So I think that is need to be derived. So let's have a look. This was the case theta, this was the h, this was the x. So this could be written as x equals to half a t square. This x we have this sine theta is equals to h by x. So from this, x is equals to h by sine theta. This is equals to half into a could be written as g sine theta multiplied by t square. So this t square should be is equals to 2h by g sine square theta. That's it. Yes. So let's take a ratio of this t1 is to t2. So if I observe this thing very carefully, this is 2h by g sine square theta. 2h by g sine square theta would be the last, and only the term I have been left with is the under root of 1 plus k square by r square. I hope this is clear. Is it clear? Is it clear? Great. So is it clear up till now? Is it? Great. Let's have one logical question. Think for it and give me the answer. That what would be the work done? What would be the work done due to friction? What would be the work done due to friction when object is rolling, on the wedge having height h? So they've asked that this is the case we were discussing. This is theta, this is the friction, an object is there, this is at h. So an object is moving in this direction, and at certain time it will reaching at the foot of the wedge. So what they want that find out the work done due to friction. We understood that in this situation object can roll because of only and only friction, because mg sine theta does not provide a required torque to rotate. So it is the friction who will provide me the torque. But now what would be the work done? What is it? What would be the work done? How will you do this? How will you? So what I understand is in this situation, please think it's a work done due to friction. Is 0. Why? Let's try to understand that this was the object, and let's suppose on this particle, because it is the only one which is in contact, a friction is acting on this direction. If friction is acting on this direction, and the next instant the particle is from here, it was initially at here, it will be now at here. So displacement in the direction of force of friction is 0. I can say that displacement of a particle in the point, displacement of a particle in the direction of force is 0. I'm talking about the frictional force. So work done equals to 0. Please remember this. In this situation, work done due to friction is 0. And that's why only I have written, if you remember the first situation, very first situation where we have derived the velocity. In this situation, Have you remember this? Yes, that that is the only reason I can write total energy at total energy, and I do not require a friction at all. Otherwise, if work done due to friction is non-zero, if work done due to friction is non-zero, then I must include a work done due to friction as well, and then I can write this total energy and total energy. I hope this is clear. So please do remember this thing, that very critical and very logical questions can be asked from this. One thing, work done due to friction is zero. Second, it is the only friction. It is the only friction which can roll the object. If no friction, that means no rolling motion. And if no rolling motion, that means it will only slide. That means it could have only the translatory motion. Direction of friction is in the upward direction of the wave, whether it is moving in the downward direction, or whether it is moving from the from the bottom to the top. I hope this is clear, and every aspect of this is clear. Is it now? Any doubts? No? Great. So let's just wind it up this session over here. This is all about the rolling motion while object is moving on the wave. In the next session, we are going to discussing the rolling motion on the horizontal surface, and different applications and different questions based on the rolling motion. So please revise this very carefully. We are on the end of the this session. It's a system of particles and rotational motion. We are on a almost on the completion stage. Yes, so please revise it from very basics, and when I say from very basics, I mean it is from center of mass. Please do as many questions as possible, because center of mass requires a practice. Moment of inertia's question should be done, because even it requires a certain logical aspect, certain visual approach would be there, and that visual approach would be created by practice only. So please do the needful, please practice a lot, so that this can be done. I hope this is clear. Please do so many questions. Thank you. Have a good day. Take care.